Hello again. Welcome to the second part of today's meeting. Our second speaker today is Mikhail Troshkin, and the title you can all read is Brown's representability theorem, which makes sense for spaces, and hopefully we will see how it works in this case. And then there's a similar theorem for spectra, and again, the idea is to explain, deduce it from the same theorem for spaces. Over to you, Mikhail.
Thank you. So actually, I'm going to do something a bit different than it was announced. So yesterday, I really thought about it, and I think that I deduced that we can prove the theorem for CW spaces and for spectra at the same time. I think I have written here an argument that works in both cases. So yeah, we'll be proving two theorems at once. And the setting is, first setting spaces. We have connected pointed CW spaces. And we have contravariant functors from that category to pointed sets. And the second setting is that we have homotopy category of sequential spectra, and again contravariant functors from that to abelian groups. And we have, well, here a part of the unidal lemma written that all the natural transformations from home functor to some x to some other contravariant functor under consideration, this h, have the following form. We take the object representing the first functor x, and we take some u in h of x, and then we simply pull it back along maps. And so we want to find some pair. I will be referring to this pair object and some element in its image under H as a pair, such that they represent the functor h. So this unit transformation is an isomorphism. And here are the necessary and sufficient conditions for it. And well, the statement that they are sufficient is Brown representability theorem. So what do we know about representable functors? Well, we know that they map cofiber sequences to exact sequences. So here I'm considering only very short exact sequences like free term only. But for spectra, they can be extended to long exact sequences. Well, and note that in the case of spaces, we in general have only exact sequence of map between pointed sets. So what does it mean? That here in the middle pointed set h of x, we have a kernel, something that maps to the base point in h of a. And the statement is that this kernel, something that maps to the point of h of a, is precisely the image of the leftmost arrow. But it may well happen that we have, say, a map between pointed sets that is a surjection and has trivial kernel, but is not an bijection. So we need to be careful about that. And actually, in some cases, it will be convenient for us to reformulate this cofiber sequence condition as Meyerowitz type condition. So if we have this diagram, we have two complexes, CW complexes, or subspectra against CW subspectra. And the intersection is also good in the sense how intersection is included into both A and B. Well, then we have this map, h of x to fiber product, of H of A and H of B. And well, it is surjective. So if we have some elements of H over A and B, and they agree on the intersection, then they can be glued together.
And why is it equivalent?
Well,
So the second condition says let's say the functor takes values in abelian groups. It says that the so the second condition says that the Maya-Vittori that the short Maya-Vittori sequence is exact. So we can form the Maya-Vittori sequence for just 1 degree, and the subjectivity condition says that this short Maya-Vittori sequence is exact.
yes, right.
Мы, значит, можем написать такой короткий кусок Мая-Виториса, и, значит, вот то, что написано во втором абзаце, это, по сути, требование, чтобы такой короткий Мая-Виторис был бы точно. И вот, собственно, все, что сказано во втором абзаце.
Yes, of course. And well, we may deduce the first point from the second by like appropriately cutting the this x-vis mapping cone attached. So we like cut the attached cone in along its like equator, and then we have it union of mapping cylinder and cone over A.
Yes, and
by a copy
how
of
to
A.
deduce the second from the first?
Well,
we need to take two short exact sequences and form a single Maya-Vittori sequence out of those two. Basically, we take first x comma a, and then b comma b intersected a, something like that.
Yes, thank you. That's precisely what I wanted to say. So, okay, and so are we clear with these 2 points being equivalent now? Is everything right? Okay. And well, the second axiom is that representable functor maps coproducts to products.
And co-products exist. Co-products of any cardinality exist for spaces and for spectra as well.
Yes. So, and Brown representability theorem says that, in fact, these conditions are sufficient. Okay, and before we get to proof, I have some remarks. So the first point is something I already mentioned, that, well, at least in the homotopy category of spectra, we can extend the cofiber sequence from a short sequence to long exact sequence like triangle. And then if we apply H to it, we have a long exact sequence of abelian groups. Then the next consideration is very important for us. So it says that if we have any pointed space, its suspension is a cogroup object in the homotopy category. So I might try to draw the picture here.
Well, it's a comonoid object, oh no, sorry, it's a co-group as well. Okay.
Okay, sorry for this awkward drawing, but we basically collapse the suspension along the equator, and we got the wedge of two copies of suspension. And well, I didn't write again explicitly the rest of structure maps, but
and by the way, it makes sense to talk about groups and co-groups because the it doesn't make sense to talk about groups and co-groups in any in an arbitrary monoidal category. But we have a particular monoidal structure, which is the wedge sum, and it's it's co-Cartesian or Cartesian. I don't know the correct terminology. Maybe Arshak can tell us. Anyway, the co-product, the product of two things is just the push out of the maps from the initial object, and this is what makes it co-Cartesian. And for Cartesian monoidal structures, we can talk about groups, and for co-Cartesian monoidal structures, we can talk about co-groups, which doesn't make sense in the arbitrary case. Значит, смысл в том, что в нашем случае моноидальная структура Кози-Картова, и поэтому в ней имеет смысл определять по-группы. Если бы у нас моноидальная структура была бы там абы какая, то значит, в ней уже можно определять комоноиды, значит, без проблем, но нельзя определять по-группе. Значит, Кози-Картова, это значит, что вот X букет Y это то же самое, что пушаут, значит, диаграммы точка отображается в X и Y. Значит, Миша, имеет ли смысл только что, значит, то, что сказано?
Yes.
Very well.
And well, functor H is above maps co-group object into group objects. Well, that's in pointed sets. And I think this is, well, at least this is because H maps coproducts to products. Like, is this property sufficient? Now I'm not sure. But anyway, we know at least that this holds and that unidential transformations are group homomorphisms.
Давайте подумаем. Значит, вот у нас есть там какая-то моноидальная структура, и значит, мы хотим понять, когда значит, функтор переводит группы в группы. Значит, и достаточно ли для этого то, что функтор будет значит, будет переводить произведение в произведение.
Ну, я думаю, что вот по меньшей мере, как если мы сказали, что в первой категории структура Коди-Картова, а во второй Декартова.
Не моноидальная, комоноидальная структура. Значит, ну, или в принципе, это не очень важно, там, что одно определяет другое, но так или иначе. Значит, ну, да, значит, Коди-Картова тра-ля-ля. Сейчас давайте чуть-чуть подумаем. Вот что такое когруппа? Это, во-первых, вот отображение, которое у вас здесь написано, сигма y обучает сигма y, значит, плюс q обратно. Ну и плюс какие-то аксиомы. Значит, дальше ну да, правильно. Значит, дальше мы берем, so we just have the co-group structure on in the source category, which is spaces or spectra, the homotopy category of spaces or spectra, and we want to get the same structure for in the target category. Well, we just apply the
Okay. And we will use this for spheres of dimension at least one. And the final remark is really just a tangent that for spaces we can drop the assumption of connectedness if we want to formulate Brown representability theorem in the same way. But the counterexample is beyond the scope of this talk, in my understanding. It involves some more involved group theory. I just want to point out that this exists. Okay, so now we come to the proof. How we are going to prove it? First, I introduce some terminology. I call the pair of x and u that belongs to h of x a pair, and if it represents h, it will be called a universal pair. And well, we know by Generalised lemma that
what is u?
I haven't written. U is some element of h of x. And it will give us natural transformation by pullbacks. So like this.
Okay.
Okay, and we call a pair P universal if the induced map is bijection just for all spheres mapping into X. And whenever I say for all indexes I, the index I will always be about dimension of the sphere. In the category of connected spaces, it will be for positive dimensional spheres. And in the category of spectra, we will consider spheres of all integer dimensions, like all possible suspensions and desuspensions of the standard sphere spectrum. Well, this is a convention. And what we are going to do, we will going to construct a lot of P universal pairs. We are going to show that they are all equivalent and that each P universal pair is universal. And then we win. And also, before going with the proof any further, I wanted to briefly discuss this example of well, the simplest application of the theorem, and well, what we will learn from the proof, that the ordinary cohomology with coefficients in some abelian group is represented by the Eilenberg-MacLane space. So
why do you assume that n is greater than or equal to? What's wrong with n? What's
to
wrong
be
with n equal to 1?
honest, I think it could be one as well. I just wanted to be careful, and I just didn't want to think what happens to Eilenberg-MacLane spaces of non-abelian groups. But I think that the argument holds as well if n is equal to 1 and G is abelian.
Okay, well, we already saw a proof of this theorem in the first talk by Jipping, and well, here's another proof.
Okay, so it really follows immediately once we know the Brown representability theorem, and that P universal objects are universal. Because we know what is the nth cohomology of spheres. It is trivial if the sphere is not n-dimensional, and it is equal to G if the sphere is n-dimensional. And those are precisely the homotopy groups.
Sorry, you probably need okay, the homology with G coefficients. Okay.
Yes. So we see that at least abstractly, the homotopy groups of KGN are isomorphic to the homotopy groups of KGN are isomorphic to the nth cohomology of the corresponding spheres. And actually, the fundamental class provides this isomorphism. Okay, since we have already seen this theorem, I don't want to stop here anymore. And now let's get to the technical details of the proof. First, we are going to construct P universal pairs. And here I formulate more precise statement than if we start with some fixed object and an element in H of it, we can actually embed this object Z into some larger object which provides P universal pair. And such that this sort of universal element U, like again, sort of fundamental class, pulls back exactly to the chosen Z that we had initially. And the construction is going to be inductive. So first we have the space X0, which is just a wedge of one copy of Z, and a copy of I-dimensional sphere for each element of H of that sphere. And then by the wedge axiom for H, we get some well, canonical tautological element in H of X0. So it's Z for Z large, and it is well alpha in the cohomology of sphere that corresponded to the element alpha in the wedge sum. And so by construction, we see that the natural map from Py of X0 to H of Si is surjective. So we get some very large space X0, but it doesn't really matter. So next comes the step of induction. So we have some space together with this fundamental class, would be fundamental class, and then we consider of kernels of the maps that pull back this fundamental class to H of spheres. And again, we do a similar thing. We take the wedge sum of all spheres corresponding to all those elements of kernels. And of course, from the wedge of spheres, we have a natural tautological map, which just for each sphere realizes this element of kernel. And we essentially glue new cells along this map of each of spheres. Or in other words, we adjoin a cone. And then we have the cofiber sequence. And from its exactness, we see that we can lift the fundamental class UK to some fundamental class in in H of x k plus 1. Okay, is anything about this construction unclear? Any questions? Okay, let's move on. Now we have for each natural number k constructed xk together with a distinguished element in its image under H, and such that all these elements U are compatible under restrictions. And then we construct the homotopy limit of the sequence. And a lemma that I will prove later says that actually H of this homotopy limit maps surjectively onto the limit of H of these things. So since we have a compatible sequence of elements UK that represents some element of limit of groups or sets HXK, we have some distinguished U. Or not necessarily distinguished, there might be many choices for it, but we get at least one. And now we see that X, this homotopy limit, and this U that we obtained from surjectivity provides us with a p-universal pair. So here's where we use that H of spheres is a group, because to check that this maps from Pi of X to H of Si are bijective, we actually show that they're surjective and have a trivial kernel. And this map is surjective because the map from X0 was already surjective. And it factors through Py of X. So if we have a surjection that factors like this, then the rightmost arrow must also be a surjection, of course. And to see that this map Pix to HSI is injective, we use that essentially the spheres are compact. That Pi of homotopy colimit is colimit of Pi's. And that means that if we have any fixed spheroid in Pi of homotopy colimit, actually its image lands in some finite step of this tower. And if it were to map to 0, if the spheroid pulled back the fundamental class to 0, then we know that in the next step of our tower, the spheroid is null homotopic. And so we see that the kernel is trivial. Okay, and here's, as promised, the proof about the lemma, about homotopy colimit. if we have this functor h, which satisfies the condition of Brown representability theorem, and any tower of sequence of inclusions, then this natural map h of homotopy limit to limit of h is surjective. And this can actually be done by Meyer-Vittorius. We form the reduced mapping telescope, and we decompose it into sort of even layers and odd layers. And then if we carefully track down what is their intersections, we see that the condition that the sequence of odd elements and even elements respect to the same thing in the intersection is precisely that, okay, maybe I should write something. So basically we have this fiber product, and this is precisely sequences UI such that UI plus 1 restricted to xi is UI. So that's sort of a tricky way to encode the compatibility conditions of limit of h xk. So this is a trick I learned from Hatcher section on the Brown representability. Okay, this is like a really tricky thing because it well reduces the statement about infinite telescope to some finite application of Meyer-Vittorius. Okay, so what we get? We have proved the lemma about homotopy colimits, and now we know that we can embed each object into a p-universal pair. So now we will be proving that any two p-universal pairs are homotopy equivalent. So first we will see that if we have maps, a map between p-universal spaces, pairs, such that it pulls back the distinguished element of one into the distinguished element of the other, it is a homotopy equivalence. Well, I could rather maybe say weak equivalence, but here I will use these terms interchangeably, I guess. And from the p-universal property, we just see that the isomorphism the composite isomorphism through h of si is induced by f. So we see that this map f induces isomorphism on all the homotopy groups. So f is a homotopy equivalence. And now we extend this to show that there are, in fact, such maps between any two universal pairs. Because if we have any two universal pairs, we can embed them both at the same time into some larger p-universal pair for h that will be homotopy equivalent to each of them. And we just compose those equivalences. So this is essentially, again, an application of Meyer Vitoris and a previous statement that each object with a chosen class Z embeds into P universal pair, such that U pulls back to Z. Okay, so now we have established some properties of P universal pairs, and here we get to the sort of crucial lemma that is really the main thrust of the whole argument, this mapping extension lemma. So what this says? This says that if we have an inclusion of a subcomplex A into Y, and we have represented some cohomology, some class in H of A by a map into X, and that element is a restriction of something that exists on the whole I, then we can extend this map F to the whole of Y. Without changing the homotopy type of restriction of this map to A. And so again, we sort of do this trick again. We glue these two spaces along A, and we apply Meyer Vitoris. Okay, I'm really sorry. I have to say that I'm sort of struggling how to present this argument in any like presentable form. It's really technical, and I don't feel like there is much to say. It's something that you should just read and think through it on your own. I'm not sure how to communicate this in words.
Well, let's see where the potential problems are. We want to what do we want to do? Well, the potential problems are we extend something and the extension exists only in the homotopy category. So there could be two ways to extend the same thing, which are the same in the homotopy category, but not the same of the nose. But it looks like those sort of problems do not appear in this argument.
Well, here I'm actually not saying that we extend f itself, we extend sort of f up to homotopy, because this is
Yes.
all we need.
Yes, we do not make claims. We do not make claims that the extension is unique. Just that it exists, and
So maybe let's draw this diagram.
And this diagram lives in the spaces for spectra. It does not make
Yes.
sense. It does not make sense in the homotopy category. Well, it does sort of make sense, but only if at least one of the maps is a configuration, and so on.
Okay.
So this diagram makes we consider this diagram for spaces or spectra. Very well.
Well, I'm not sure, actually. The problem is that indeed this inverse map from x prime to x may only exist after the localization in the homotopy category. So
Yes,
this
but
arrow.
the co-limit on the left does not make sense in the homotopy category. In the homotopy category, very often we do not have any co-limits at all. We only have homotopy co-limits which do exist, and then we need to ask whether or not the co-limit of the diagram is the true homotopy co-limit.
Actually, thank you for clarifying this. I was just sloppy with my notation, and actually, homotopy limit is precisely what we need here.
Okay.
So by that, actually, this is what I mean by that.
So the homotopy co-limit sometimes can be computed by taking the co-limit of the diagram itself. But to do this, we need to assume that, well, as actually we talked about in the beginning, that all objects are cofibrant, and at least one of the arrows is a cofibration.
Yes, and I think this is here. It's perfectly fine to just replace both maps from A by cofibrations, and this will not change anything.
So if we replace the diagram, the whole diagram, by another one where all maps are cofibrations, then we can just take the co-limit of the diagram itself.
Yes. Okay, so
so this X union Y is to be understood in the homotopy sense.
yes. Thank you for pointing this out. It's just a bit sloppy notation. Okay, so what do we have here in this diagram is this composite map from X to X is made so that is identity up to homotopy. And so if we follow all these arrows, we see that the resulting map from A to X on the right is the same up to homotopy as original F. because we compose F with identity in the homotopy category. Okay. Are there any more questions about this diagram? Because this is really the crucial step, and after we do it, there is really just one more step to deduce that P universal pairs are universal. Okay, and well, I guess I have to erase this, unfortunately.
Well, probably it would make sense to expand the nodes a little bit. And,
Yes, I will. When I send you the notes, I will try to include the diagrams.
okay.
So, and now we use the mapping extension lemma to prove that P universal pairs are actually universal. So first we see that this natural transformation phi of u is surjective. And this is simply the mapping extension lemma for a point included into the space under consideration. So trivial class in H of point, which is just 0, or well, the base set of one base point. We can extend this to any class, to a mapping F tilde, which pulls back from U any desired class on Y. And to show that phi of U is injective, we actually will show that if two homotopy classes of maps from Y to X produce the same element of H of Y under pullback, they're actually explicitly homotopic. So what we do here, we have those two classes of maps from Y to X, and then we construct the cylinder over Y, and we take a map on the top end of the cylinder, which is F0, and on the bottom end is F1. And we can apply the mapping extension lemma and extend the mapping to the whole cylinder, which provides the desired homotopy. And since two maps, F0 and F1, are homotopic, they coincide in the homotopy category. Well, and that's all. We have shown that the natural transformation phi of U is surjective and injective.
Okay, very well. Are there any questions? Well, it looks like there are no questions. So, Mikhail, thanks for your presentation, and please send me your notes, possibly after including some more things we talked about during
Yes.
during your talk. Okay. Turn off.
Okay, thank you.